Hi, everyone. Thank you so much for inviting me and for being here for the talk. I'm very excited uh, to present some of my students' work on understanding and leveraging diffusion model representations. Um, so here is my research group. Everything that I'm going to talk about is work done by them. So very grateful that I have a very nice group. Um, at a very high level, I can summarize the themes of my research into three blocks. One is um, understanding how generative models or foundational models encode different semantic information into them. Um, can we use this understanding to improve the generation capabilities or the reasoning capabilities of these models? So understand and leverage has been the theme of the works that we've focused on. So doesn't need an introduction. Generative media is everywhere. It's something that's taking over social media and creative applications and many other very fun world. If we are an astronaut or an alien floating up in the sky, the way before learning what diffusion is, the way I perceive this as I'm starting from something that's pure noise, absolutely no structure, and getting to a world where is such beautiful structure, the reflectives in some of these objects, the expressiveness, the unrealistic compositions also happening so nicely. So how did we get from just noise to this well-structured, semantically rich visual medium? So we started off, there was a world where we were able to generate images only using GANs and variational autoencoders were sort of the building blocks. And the goal there was to be able to generate one single object with an okay visual quality as long as the core aspects of what that object represents are captured. And then we moved on to faces. There is more detail to be captured, but notice how small or tiny the resolution that we were aiming for was at that time. So the metrics that we cared about were we just wanted to get something that looks realistic and then has decent visual quality. Those were our goals. And then lots of things happened. As we were able to scale on the algorithm side, there are better models leveraging the diffusion and autoregression techniques. And that's all of these data compute and modeling design, all of these got together and helped us get to where we are right now. So that sort of makes it clear that, okay, look at these generations and it looks like, okay, the photo quality, the visual quality looks really good. The realism is there. So is there anything left or for us to care about? Turns out a lot more things. Is there temporal coherence, something that I've talked to some of you, if you're trying to generate a very long form video, is it coherent? Is the person or any action that's happening has to be consistent and coherent over time. Anything that's being modeled by these videos have to be physically plausible. It should be controllable. Me as an end user should have the knobs to tune to make the generations more controllable. For this talk, I'll focus primarily on, I do want to build models that generate extremely rich, visually rich photorealistic quality, but I also want to get some sense of what's happening underneath these large models. So that would be the primary focus of the talk today. And again, please feel free to interrupt me at any point. I'll also be pausing, but like I hope like the talking points like are do come through. So let me know if I need to pause. Um, so why should we care about like interpreting these models? I mean, they're doing such a great job and like generating these creatively like rich visuals. So beyond just like curiosity, the intellectual curiosity, I do believe like better understanding leads to like better models and better algorithm design, smarter, maybe more data efficient algorithm designs. Some of you like already work on model understanding. There are many ways to like approach it. You can build post hoc techniques where like the model is already trained. You can build a fully interpretable like model, like something like decision tree, or somewhere in between where you have a model and then you try to probe its like activations, its weights, and get a sense of like what's being captured, encoded within this model. Um, that is that has been our approach that I'll talk about today, where um, the model is already trained. A lot of things are unknown, but the goal is to be able to extract its activation patterns and see if there is if that helps us understand how information is like captured in them. Hi. Um, How do you judge your wisdom? Yeah, no, great question. Like one key motivation is to it's mainly coming from like a being curious about. Mhm. It assumes that we've yeah, the choice of model, like which model to understand, it has primarily been driven by what's the model that's being most widely used for different applications. So in the case of at the time, like if it's a text to image generative model, the models have been the ones that are very widely adopted. So let's understand how these models work was the motivation. Um, so interpreting models is like not it's something that we've been doing for like several years. We started off with like when convolution networks were getting popular, one line of work was let's understand what is being captured in these convolutional like filters across different layers. So there has been work which built different tools for this visualization. And then when like there was this race of using transformer based architectures, there was again like this interest or drive to understand what's being captured in these models. And there were like different like visualization techniques or probing techniques. So now when it in this particular case, we look at a family of diffusion models where like the goal is given during inference, given a text prompt, these models will generate an image that reflects the text prompt. So a couple of challenges when it comes to analyzing diffusion models. One is it's sequential in nature, just the way it's trained. You take an image, you add noise, and then the goal is to like remove or predict the added noise. And then this happens sequentially. So there is like sort of an unrolling of the model that happens. Sorry. So in addition to just the model at a current state in time, there is also like different maybe model activations or model patterns at different um, uh, times during the denoising process. So that adds to the complexity of sort of the search space that we want to like understand. And then again, like, yeah, every noise scheduler has its own like quirks, and that has an impact on what the model is learning. So these two do make the problem of studying a diffusion model like more challenging compared to studying like transformers or like convolutional networks. So this is our goal. Like, how do we, like, given like a popular diffusion model, like what should be our tool to study this? We've seen autoencoders primarily being used as a tool to one tool that it is used is to compress the signal. So take an image, which is 512 by 512 times 3. It's a large, rich, dense signal. Can we represent it in a much compressed, like latent space? So that has been like one popular application amongst other applications of autoencoders. This is called as an under complete feature space because you're going from a large space to like a much smaller one. Something that has been used in the literature is k-sparse autoencoders. So as the name suggests, like it's a sparse autoencoder. So you go from like a given feature space and project it into a much larger space. And the hypothesis is that if the projected space is large enough, then maybe all of the interleaved concepts can be broken into monosemantic concepts. And I'll talk about what monosemantic concepts are in the next slide. So at a very high level, given a pre-trained like diffusion model, we'll extract features from a given layer at a given time step. So let X represent that. These are typically polysemantic in nature. By polysemantic, I mean because we've compressed rich semantic information into like 1024 or 2048 dimension, every I would say every neuron can capture like multiple kinds of information or multiple types of concepts at the same time. So we take these features and we project it into a much larger, sparser embedding space. And the goal here is that everything that's polysemantic, where like information is like interleaved, hypothetically can be broken down such that every neuron systematically represents only one concept. So that's the hypothesis. So if we have such an ideal like projection space, the hope is that if the concept that we're trying to learn is like blue car, for example, so maybe one neuron will represent just blue and the other neuron will represent the concept car. So that's what we were like going for. And the way this can be like learned or imposed is a typical like sparse autoencoder learning process where you want to reconstruct the signal that you're trying to project, but by enforcing sparsity in the learning space. And top K is a trick just for faster convergence, where in every like training step you retain only like the top K highest activation units just to introduce some non-linearity into the training process. So hopefully, yes.
What is the free?
Yeah, this is just like a weight matrix and a bias term. So this is something that we normalize the signal. So there is, yeah, I should have introduced. So the data is centered before we try to project it.
And then there's some NLP kind of.
Yeah, yeah.
And the top K is for nonlinearity, not for sparsity.
For it helps both, like when we try to, so there is a sparsity, like L1 loss also helps you with it, but top K has been like studied in prior work to make it converge faster and also like introduce like nonlinearity. So it does both because we retain top K and set the rest to 0. So it is doing the sparsity. Yeah.
When you use this kind of sparsity to try to disentangle the different concepts, do you have any like are there nice properties that emerge about the composition? Like when you start to like add these concepts together, like for example, like as you said, like blue car. I mean, maybe there's like certain like language is very like contextual, right? Like maybe blue means something different if I add it to a different word. And so yeah, I guess I'm just wondering like, can I just naively like add these element wise and like I should get like if I have blue and car, then I'll get a blue car, or do you start to see weird behavior from the compositions?
No, that's a great question. So if this space is learned perfectly, then we should be able to combine, just light up this neuron with this neuron, and we would see like a very nice composition without any artifacts. But in reality, not just in this work, and other papers have tried to see that this is, and I'll have some visual like examples where this does do the separation reasonably well, but there is some leakage of concepts. So when you try to add two concepts, we would definitely get what you're aiming for, plus some additional like side effects that are not exactly intended. I have like a few examples where we've seen this, and I'll get to that. Yes.
Is there some like correlation between size of the input dimension and the choice of the
Yeah, absolutely. So not K, but there is something that we had to choose, like how big should this be? This over complete feature space. It is a function of both the dimensionality of input, like X, and also how rich this text embedding or like the visual embedding is. K is something that we had to like, was a hyperparameter that we had to like sample and choose.
but what was the order of like K?
In this work, K was like 64 to 128 were the two numbers.
Question.
Yes.
How is this related to the fact that it is a diffusion feature? Right. That is noise, because it kind of works for any.
It does. You're right. It does work. It's a hammer that can. It's not specific to diffusion. Can be applied. You can replace X with anything. And there are works where people have like primarily used this on LLM features activations. So nothing diffusion specific.
But the fact that it's noisy, does that make it different?
It does. So we go from signal to noise during like training. So and so we do see that this tool stops being useful because like, well, the feature is so noisy that it won't be able to learn anything after like few time steps, like after I think 200 out of 1000 time step training process. But it is able to extract something even at 200, at t equal to 200, which in itself was also surprising for us. Yeah. Did that answer your question? Okay. So yeah, we ended up using sparse autoencoder as like as a hammer tool to explore like a lot of different questions. First question that we were interested in is, because of the architecture, the way the model is designed, like there is some hierarchy of like semantic information in like CNNs, and like some way the information is encoded in transformers. What happens in like diffusion models? Like, is there certain like property that evolves? So to do that, so I show a unit like architecture, but this can be like DIT, it can be anything. Everything is pre-trained and frozen. And I'm sure most of you like know the pipeline. We take a bunch of images. It in stable diffusion, it goes through an autoencoder, and that latent embedding is what is like noised and denoised. So in this particular example, we take images from Oxford Pets dataset. So lots of pictures of like different breeds of cats and dogs, like more fine-grained data. And we pass it through this pre-trained network. When there is like no noise added to these images, let's say. So time step 0. And then we extract features of these models from like different layers, let's say from the bottleneck layer, and train this one layer like k-sparse autoencoder on them. And then once trained, when we started probing this network on like, okay, for this particular neuron, what are the top 9 most activating images? Like what is this neuron activating the most for? We found that this neuron was learning very coarse grained information. So there was like neuron 1 would light up for something that has similarly positioned objects, like all of the could be cats or dogs, anything that's like on a couch, for instance. Or there would be another neuron which would be like lighting up for any animal on grass. So very similarly positioned objects, so very coarse information. We repeated the process again, like the same image data set, like went one layer up, extracted features, trained the k-sparse autoencoder, and now the signal was getting a bit more like granular. So it was, at least there was one neuron that would fire up for only dogs. There would be another neuron that would light up for similar looking like cats, for example. One layer up, this was like the, again, like repeat the process, pass these images, extract features from this layer, train a k-sparse autoencoder. And then this was the k-sparse autoencoder that was capturing very like nice fine-grained information. So it almost as good as breed classifier, like animal breed classifier. So there was one in the k-sparse autoencoder, there would be one that would fire up for like a particular breed of like dogs, and there would be another one that would like light up, have highest activation patterns for another breed of cats. After that, the signal started like getting diluted. So again, like so we went from coarse to moderately coarse to fine, and then it started again like flipping to like relatively coarser information. So one takeaway that we have here is, even though we didn't explicitly enforce this, there was some hierarchy of semantic information that got captured in these models. Like they did go from like coarse grain to fine grain. And then the reason for the signal to get diluted as we went further up was because now those feature representations were trying to align themselves with the final objective, which was pixel level denoising. So there was some structure, and then later the structure was getting like broken down because the objective function was having a higher impact. So hopefully that was clear as to like how we probed for like the visual information and the findings. So I showed examples using k-sparse autoencoder, but then it felt subjective because I can see what I want to see when I'm looking at like top 9 activation units. So another thing that we did was we passed these like highly activating images through a VLM and asked if those models saw like something common. Well, what's the one common semantic property across these. So that was another way of like not having like a confirmation bias. And the third way that we did this is like the classical way of like extracting these features and maybe like training a model on top of them and trying to see how they perform on different tasks. So our hypothesis was certain layers were good at coarse tasks, certain layers, features from certain layers were good at like finer grained tasks. So to study this, we took two data sets. One was fine grained, like birds or Oxford pets, and the other is like a coarser data set, maybe like ImageNet or Caltech, where not ImageNet, Caltech. And again, like repeated the process, extracted features from different layers and studied the performance. So we did see that for pets and aircraft, like the blue and the purple, we did see that upfeed one was giving like highest accuracy values, indicating that these were the features that were more discriminative on the finer grained tasks. But for Caltech, which is a coarse data set, it didn't really matter. Like the bottleneck features were good enough. It captured the information that is needed to do the very coarse like class separation. So again, like same finding, but like validated through like three different like approaches. The other question, before I move on, any other questions on this? Okay. So another question we were curious was like, is the information sort of encoded differently in different diffusion architectures? And there is stable diffusion, which is like unit based, there's VAE, and then there is DIT and flux, like different models with different architectural choices. How does that, but the end task is the same. The final objective is still like pixel level denoising. So how does that impact how information is packed in the model? So that was our question. So very quickly, the way we did this.
Response to what the diagnosis resolution.
Can you repeat again? Sorry.
Is the diffusion corresponds to the same thing as we used to call different scales, different spatial resolution.
So not quite.
He has to make a connection to the work that was done.
I agree. Yeah, I agree. I should have clarified by diffusion, like different architectures. I was referring to the underlying network architectures that are used for the same task of like diffusion denoising. So UNIT is an architecture that is convolutional based. And DIT is another like model, does the same diffusion denoising, but uses transformer based architecture. So it's not the scales as you were referring to, it's a different architectural choice. Okay.
But I think she was referring to the previous section we just walked through. We had the different layers.
Oh, I see. No, so those is talking about them as like layers. That's
Yeah.
different from the architecture. The diffusion architectures, I mean, is it like convolution based or is it like transformer based architecture?
Like they do the coarse grain and then fine grain. Does that correspond to the idea of like resolution, speed?
It's a different semantic space. So it's not just space, but it's actually a different level of representation. So it's not just frequency space. It's more a representation space. So one may be like face versus no face.
Because you have a little table, what the different representation, so that we understand that we are talking the same thing.
You can think of semantic as who is your similar action space on your instruction.
So semantic starts with
So yeah, so what's the similarities? For example, two faces are similar even though the color is different. So there will be one level of representation. Or the other level is that they have the same fur, therefore they're similar. That's a different semantics.
Thank you. So the question here was like, people, like, we use different architectural choices, but the end task and goal is the same, which is generation. How does that impact how visual information is backed? And the way we try to do this is, in addition to k-sparse autoencoder style probing, one thing we did is again extract the features of, let's say, this particular image, and then project and get the top 3 principal components just for us to visualize. And what we found was, again, with especially in the upfeed one, or like the upper middle layer, there was a cleaner signal, and like information was more spatially localized compared to a DIT based architecture which uses transformers, where again there is global attention that kind of dilutes how granular these features could be.
Sorry, what do the colors mean in the maps?
Just one, yeah, I should have clarified. So
Oh, sorry,
each-
PCA, sorry.
yeah, so one
PCA.
color indicates like one component. And the goal was to understand like the k-sparse autoencoder visual probing showed that there was no systematic coarse grain to fine grain pattern in DIT as we saw in unit. So when we visualized this way, it was because, again, like the information was not easily separable when we use DIT. Go ahead.
In the DIT one, it's still the foreground background look very they always different colors.
Yeah, it's just not as clean. They are decent. Is that what?
Yeah, I'm saying, yeah, basically all foreground are red and
So the foreground, background, the coarse signal is really good. But when it was trying to separate out like
different.
the objects within foreground, it was slightly easier or cleaner in the unit space. But then after, when we go to like higher blocks, the signal gets more diluted because it starts to align with the overall objective. We tried a bunch of other things. Again, like I don't have it in the talk in the interest of time. So one thing that we tried was like information packed at different time steps, something that you had asked about. And our takeaway there was even up until like even some amount of noise, the feature space was relatively robust. And once the amount of noise gets really high, that's when we just lost the signal and couldn't find any pattern. In this question, like, well, it did seem like these diffusion features were capturing like semantically rich information. Can we leverage it for like other tasks, like other reasoning tasks? So maybe some of you know this, like it's Lava. The framework is again like give like an image and ask for a particular task, like image, and it could be a VQA based task or like question answering. And typically under the hood, people use clip as like the vision feature embedding. What we found here was that because diffusion features were capturing rich semantic like information, augmenting just clip with diffusion features helped in improving the reasoning tasks by 3%, which was significant at that time. Surprisingly, we found Dino was not helping clip as much. So we ran this because we thought, well, clip maybe has such global information that adding anything to it might just benefit the performance. So just to see if we added like another feature representation, will that like make a difference? And we did find that for this particular task, diffusion seemed to like clearly benefit this particular task rather than like adding Dino.
Yeah, so are you fine tuning a TLA on the extra features?
We do add like adapters on top.
Oh,
And then like combine the features and feed them to Lava.
I see. And the diffusion feature is just for image generation. It's like a stable diffusion.
So these we use them just as a out of the box, like pre-trained diffusion model, pass images through them and extract like a visual representation. Yeah.
Sorry, also, is this saying adding Dino actually to clip actually hurt performance?
For this particular task, yes. So yeah, in this work, which will be presenting at ICCV, studied different questions where like what's captured in different diffusion layers and like across different time steps and also across like different architectures like convolution based or like transformer based. We did study other things which I didn't share about like can this if these features are so useful, like can we use them for other tasks? And one example was reasoning tasks, but we've also seen that they improve like OCR, like spatial reasoning and like just general like classification tasks. So yeah, like we have the code and the paper, like feel free to like give any feedback or thoughts on this. 10 more minutes. So the first module was like get a deeper understanding of the model towards the goal of helping to design better algorithms. One application that we were interested in is if the overcomplete feature space can learn different concepts, then can we either dampen a particular concept or amplify a particular concept and during inference, and can that lead to like more controllable generations? So this has two sort of arms. It does throw a light on like if the feature space is interpretable. Beyond interpretability, like it also gives you a knob to tune to see its effect for controllability. So this is the standard like diffusion pipeline during inference. Standard inference pipeline, you provide a prompt, like go from a noisy signal to like an image. So as the first step, what we did was we took text embeddings and we trained like a sparse autoencoder, just as how like I talked about earlier. And one use case was to train it on like unsafe prompts, but this can be flipped out and we can train it on any corpus of text. The application here was like to remove any unsafe generation. So that made us like train on these things. So take the text embeddings. Hypothetically, if this is trained in a nice way, where this feature space is separable, then there could be one or two neurons that activate the most for like one particular concept, let's say nudity, and there would be like one neuron that would light up, that would capture the concept of like violence, for instance. So we have this and we have this. How do we combine those two? So during inference, let's say you as a user get to decide what you want to control. And in this scenario, like I want to be able to remove a particular concept from the generation. So extract the text embeddings, project this into this over complete feature space. And I know ahead of time what nodes correspond to, like the concept nudity. And I dampen the activations for just these two neurons. And then I project the signal back into the decoding space. So the goal here is, if we've like separated out the feature space nicely, then we should be able to capture most of the semantic information and only remove the nudity concept from the text embedding. And then we combine that with the original prompt that was provided by the user. And steering strength is a parameter just to help us understand how strongly we want to like dampen a particular signal or how strongly we want to amplify a particular concept. So doing this operation, we were able to manipulate the text embedding by removing like the concept that we wanted to remove and still retain most of the other elements in the signal. Yes.
So the operation that you do is just an element-wise sum
Element.
of the original like text encoding. Does that usually work quite well, or like are there any weird interactions that you see that aren't very as intuitive?
It did work. Yeah, it works quite well. Yeah. Yeah.
So I thought the feature space you work on is the image feature space, but here you're operating on the text
Yeah.
feature space.
So like you rightly pointed out, Case, there's nothing special about like a sparse autoencoder that makes it for diffusion.
Right.
You can use it for any embedding space. And in this particular case, this one of our motivations was to make this as generic a tool as possible. So if you have worked on like generative like text to image models, it's the text encoder that sort of remains relatively similar. Like people either use like clip or T5, but it's the vision space that changes.
Do you need to pre-select the neurons based on like your query concepts, what they fire, or?
No, like once you pass the concept of choice that you want to steer, you identify, okay, here is the neuron that has the highest activation, that consistently has highest activation for this particular concept.
Like basically just query any concept.
Yeah.
And you will see what neurons are most active.
Yes.
And you modify those.
The activations that of only those.
Only those, but actually the decoded feature is a dense feature, but you only change the field that is the largest, like the highest magnitude.
Exactly. Yeah.
And then I see.
Yes.
So how does one be creator of the speaker control the strength?
Yeah. Right now it's something that you have to select for different concepts. So that's something that would be nice to avoid in the future, where like for depending on the concept. In this particular case, as I like you get to choose like how much, like how strong like a particular like concept needs to be introduced. Yeah. It can go like either positive or like negative. Is that, yeah.
I have a question. Since you use addition to steer the text prompt, is it possible to deliberately modify the text prompt so that addition will be negative during this?
Yeah, and that's like a very common way of adversarially attacking like these models, because they're so like there have been works where people have learned the best way to modify like fewest number of like um, neurons and their logic values to be able to jailbreak a particular model. So yeah.
Okay.
Um, so this is again like something that um, based on like the k-sparse autoencoder that we show here needs to be trained once on a corpus of like whatever concepts that you wish to like add or remove or like alter. In this example, like we trained a sparse autoencoder once on like different photographic styles, artistic styles, and then applied it to a variety of different models. Any text to image model that uses, let's say, clip as its default encoder, we were able to plug it in and see how the steering strength has an impact on the generation. Here is on like Flux, which at that Flux one at that time was the recent one. Again, like as we were able to in like increase the magnitude of the steering strength, but on the in the along the opposite direction, we were able to remove the concept more strongly. There are, I mean, controllable generations, like people, there's like a lot of active research, and we were able to see that the typical pipeline is like train different LoRa's or adapters for every concept that you want to add or remove. But in this case, it's just one k-sparse autoencoder trained once, and you pick the concept that you want to steer, as long as it's represented in the corpus of like text. There will be like some activations, neurons that can be like dampened or altered. So this was like an interpretable way of like offering more controllability. And as I mentioned, it was more efficient, more a plug and play like tool. And this was work done by Dahe, my student. So we are at 3:50. Do you? How much should I jump into the
We
committee?
can keep going for a few more minutes.
Okay. Maybe very quickly, just building on to the theme of how else can we use this knowledge that there is some way that these models internally represent or arrange the semantic information within them. Here is something that we found where this is a very different application, domain generalization. And just to bring everyone onto the same page, the goal is that there will be images coming from like different domains, maybe similar task, but different sensors were used to capture it, or different robotic arms were used to do the same task. And the goal is to be able to like build a model that generalizes across different domains. And what we found was, again, like DID, which is a diffusion generative model, that seems to be class agnostic and was able to capture like domain information implicitly without having any explicit like training. So here is where you'd see, so every color and shape represents a particular domain. And you'd see like these domains seem to be naturally nicely separating out, while other features like clip and MAE are more object centric or class centric. So there is just more domain agnostic feature space. So this is interesting. Like, can we leverage it? So this is probably like a very high level overview of how domain generalization like algorithms work. Is they train on like a pool of data. The goal is to be able to like learn a function that hopefully generalizes to unseen domains or like across like different domains. What we do is just like one additional step. We try to extract, again, take a pre-trained like diffusion model, let's say Deepti, and do apply a simple like k-means clustering. And we found that this one trick helped in learning like a nicely separable like domain information for free. And then we just append the centroids of these clusters to the features. So everything remains the same. It's just discovering this domain information that's already there for free and adding it to your pipeline. That was the only like small change that we did. Surprisingly, so there's, if you're familiar with the domain generalization, like there's just like such large bodies of work making like small tweaks and data augmentations and tricks to improve the generalization capability. But this was very nice to see that this information that is already out there for free, adding that led to like a boost in terms of like the generalization performance. So just to be fair, we also wanted to add like other features to see if it's just any signal, any additional visual signal might push the performance. Is it that, or is it really like something more richer that's being captured in these features? And we did see that, I think, depending on like different domain generalization tasks, overall like diffusion features do capture like something domain specific and class agnostic that is helping this particular task. So again, the takeaway is augmenting this domain information from like the diffusion space leads to like better domain generalization. And this is a nice departure from like the standard tasks of like getting explicit like domain labels or other data augmentation techniques.
Sorry, so the domain, where did you get the central? It's from the generative models on the specific domain or what?
So this is domain agnostic. So during training data, we don't have access to how many domains.
Right. Okay. So you just cluster the diffusion feature.
Yes, exactly. Yeah.
And add all the centroids, right? All the cluster centroids.
So I know which image fell into which cluster. So for that particular image, I would only append its corresponding centroid. So if there is image one that went into this cluster, only that centroid. Centroid is just so that there is like a more unified representation.
It's a hint on which cluster you're in.
Yeah, exactly.
It's like telling it's which domain you're in.
Yeah. All right, so the goal here, like we talked about one tool, which is k-sparse autoencoder, using it for understanding visual information, and one application where we use the same tool but on text embeddings to offer controllability. And also like this was an outcome of like the findings from this paper where we saw, okay, these features seem to be really good at like domain information. So augmenting it for like other tasks such as domain generalization. So something this ties back to your point earlier. You do see at a high level that, okay, the steering seems nice, but if you look at the arm of the chair is missing in like both models. Arm of the bench, not the chair. And yeah, there's supposed to be like a building or so things did depart. So it's not like a nicely completely separable like space. There is some concept leakage that is happening where all I had asked for, okay, let's introduce the concept winter, but that is happening, but it is also introducing these side effects that we don't want. So why is that happening, and can we just make it more local, is like something that we want to like study closely. This is something that one of my students is looking into. Do you know what action is going on in this? This is a
person is lowering.
squad. Yeah. So it's a classical experiment in visual neuroscience called Johnson experiments. When we asked a bunch of models this, then they did say that there's like no motion. It's like series of frames with like white dots and black background. So even the best closed source models are not able to like capture the information, which makes sense. There is a lot of semantic information that is stripped out of, but we are able to somehow like make the connection. So how do we like how is such signal like interpreted into the model, and like will it help if the model understands these complex like examples also is one thing that we're talking about, and a more like friendlier example where we've written some hand digits and like rotated it in different ways, and even those like the model was able to like not guess that these two are just like rotated versions of each other. So trying to understand again like why is this happening, and like yeah, does that help us design anything better differently? Yeah, again, like maybe like jailbreaking is another like example. Like, is there like a common circuitry that always like lights up when someone is trying to like give it certain adversarial inputs? Can we use sparse autoencoders for like just making them like safer? Something that a lot of other folks are also like looking into, but understanding this is another direction of interest. Yeah, that's all I've got for today. Like, thank you for all the questions. I'm happy to take more.
So given for the Nudity program, if you have a prompt and this like says specifically like Dataset is also new, and it directly contradicts your negative, I guess, whatever you're conditioning it. How do you know like which one's gonna win out since you're just concatenating them?
That's a good point. My hypothesis is we would have to use a higher steering strength to eventually have the nudity removed, but it might come at a cost of like other things getting impacted. So hard to tell. Yeah.
Maybe a different method, like just concatenation.
Yeah, maybe. Yes.
Actually, kind of related to that question, I feel like there's a slight difference between the first and second word, because the second is like the sparse encoders on the text development condition. And
Yeah.
the first one is on the image features.
Yeah.
And it's like if the image features, this decoupling can be used to control, for example, then if you directly interfere with the feature, like the image feature part, and then you may not need to compete with prompts, conflictions.
No,
To tie the two closer.
Yeah, I agree. I think an ideal world would be where we learn on both separately or individually and see if something that's not explicitly see here like nudity is something that's not explicitly like prompted in the text space, but it did it did get generated in the image space. So having something in the joint space or separately and trying to identify commonalities would be helpful in handling the scenarios that you both are talking about. I agree. Did that answer your question?
I agree. But I do think there's a challenge there is how do you interpret the noisy states? I'm not sure if it's true for image diffusion. It's like a lot of the most like the high level concepts got kind of determined in the early on stage when the state's relatively still noisy. So I think that actually will make it even harder to control. As you said, noisy states are less easy to decode.
Right. I see your point. So here, maybe you're talking about like at what stage to interfere, because
Right.
different stages, some of them only are more sensitive to coarse grained details, while some of them are more fine grained. Yeah, that's definitely is a challenge. Like when we don't know when to interfere and with like what steering strength at what time step. Yeah. Any other questions? Any other questions? Thanks again. Yeah, no, thank you. Thanks for the great questions.